Swayam Prabha. Digital India. Educated India.
We return to our discussion on phase equilibrium, and in this lecture I would like to draw your attention to some kind of transition between the phases. So we'll discuss how one phase can be converted to another phase and what are the guidelines behind it. So that is the thing that we would like, that is the thing that we would like to discuss in terms of certain equation that we call the Claperon equation. So Claperon equation describes some kind of phase transition that we need to do. So that it is basically, so we like to understand the transition between the phases or phase transition. First step to understand the phase transition. So we know that if phase is described by a chemical potential at a temperature and pressure. So for a phase described by a chemical potential mu at, so say there are two phases, say phase described by mu, that is chemical potential. So for the two phases alpha beta, say I have two phases alpha beta, say alpha and beta may be solid or liquid or gas, anything. So if I think that alpha to beta is solid to liquid, then alpha means solid and beta means liquid. That's the thing. So between two solid phases, for two different phases alpha and beta, we assume a coexistence. That means mu at alpha at temperature and pressure is equal to mu at beta at some temperature and pressure. This happens when we consider the melting point or boiling point. So at this point, you have both the chemical potential in the two phases are equal. So that is the thing we are reproduced here. And now this is true for any general, for any two specific phases. That is the most general equation. So for two phases alpha and beta, we assume a coexistence and we can write down this equation. Now if we change, say temperature, say if temperature is changed to T plus dt, if temperature is changed to T plus dt, then we have a new equilibrium. So for that new equilibrium, to restore that new equilibrium, we will have to change the pressure. So there will be a new equilibrium. To restore the equilibrium, we need to change P to T plus dP. That's the thing. So if I change my T on both sides, then something will happen. It will be disturbed. This equilibrium will be disturbed, and then to regain that equilibrium, we must change it to some. So for this, mu alpha goes over to d mu alpha Tp, and that is equal to mu beta plus d mu beta Tp. That is for the new equilibrium. This is for the earlier equilibrium, this is for the new equilibrium. This has to be restored. Now you see that because of this equation, that because of this condition, so automatically it follows that d mu alpha Tp must be equal to d nu beta for Tp. Now we recall our master equation for understanding the phase equilibrium. So refer to our earlier equation that we derived, that is d nu equal to V Tp minus S molar entropy times S d V dP minus S dt. So this will be true for each of the phases. So this was the master equation that I referred to for understanding the basic things. Now if we apply it to this, so this means I have a V alpha dP minus S alpha dt, that is equal to V beta dP minus S beta dt. So this means what? Say if I consider a phase transition, so consider a transition from alpha to beta. So I write it that V beta minus E of alpha times dP, that is equal to S beta minus alpha times dt. So this gives me a very important relation, that is dP dt, that is equal to delta S divided by delta V. Now you see that I am using the left hand side the differential quantities, but these changes are real finite changes. They are not the differential quantities. So this is the molar volume change between the two phases as I go from alpha to beta. Then this is the molar entropy change. So this is molar entropy change for the beta state and alpha state. So that is the difference is the delta S, and this is the molar volume change between the two phases dV. So this equation, so delta S, delta V are finite, not the differential quantities. And this is called the Claperon equation. So it means that if I change my temperature, I will have to change my pressure also, so that this equation has to be satisfied to get a new condition for equilibrium. That's the thing. So this is a basic equation that guides my phase transition. So, so let us now consider the specific cases. For example, we first go over to liquid gas transition. So specific cases. Liquid to gas transition. So for this, we rewrite dp dt equal to delta S by delta V, and this means the delta S, this is a process of vaporization, that is liquid goes to the gaseous state, so there will be entropy change for the vaporization. So it is, I write the subscript vaporization. Vaporization, this is also vaporization. Now what is my delta S? So delta S is basically delta Q reversible by T, and in this case it is basically delta H for the vaporization by T. So this means it is just delta H vaporization divided by T and times Vt. And what is Vt? What is delta T? Delta V. So what is delta V? Say V of the gas minus V of the liquid. G and L stands for gas and liquid. So this is my delta V. So this gives me the dp dt, that is equal to delta H for the vaporization divided by T times del V, that is V of G minus V of L, that is equal to delta H of vaporization divided by T times approximately equal to Vg. If I write that Vg, volume of the gas, is much greater than volume of the liquid, and I rewrite it as Vg equal to V, or I write just Vg. Now you use the ideal gas law at this point. So use ideal gas law, that is V equal to RT by P. So if this is so, then we have dp dt P dt, that is equal to delta H by R, there is a T here, T by P. So this gives me, that is equal to delta H by delta H times P divided by RT square. So it is dp dt equal to 1 by P delta H for vaporization divided by RT square, or this simply gives us d ln P dt, that is equal to delta H vaporization divided by RT square. This equation is extremely useful, and this is called the Claperon equation, and it applies to liquid gas transition, not the other cases. So it is basically applicable to liquid gas transition. And if we integrate between, say, so integrated form, for which I do here in this way, dlnp equal to delta H vaporization divided by R, integrate between some T0 to some T, 1 by T square dt times integral some P0 to P, then say P0 is the normal at 1 atmospheric pressure, and T0 in that case would be the normal boiling point. So if for P0 equal to 1 atmosphere, T0 normal boiling point. So this gives me ln P by P0 equal to, or I just, since P0 is equal to 1, I may write ln P equal to delta H by minus, then it is 1 by T 1 minus 1 by T0. So if you plot just ln P versus 1 by T, that gives the slope of this curve. The slope is basically delta H by R. So I can calculate my delta H, or the heat of vaporization for this evaporation process or the liquid gas transition. So with the help of Claperon equation. So what we did here is basically a very simple thing, that we have the two phases. If they are in equilibrium, they are in coexisting in a under certain condition of temperature and pressure. That means we have, say, a normal boiling point at 1 atmosphere, and if I change my pressure, I will have to change the temperature, or if I change the temperature, I will have to change my pressure to arrive at the new equilibrium. So new equilibrium is the following. So from that change, and with the help of that equation for change of chemical potential, we arrive at the Claperon equation, and when applied to gaseous state, you get this Clausius Claperon equation, and you find out what is basically this delta H for vaporization. So fine, this is true for a liquid gas transition. Now if we go for different a different transition, so solid to, if we now go over to another specific case, that the solid to liquid transition. That means we start again with this equation dp dt, and that is equal to delta S, and in this case there is a fusion process. So for the fusion, I write it a delta S of fusion divided by delta change in molar volume, and that is for fusion only, and for the transition from solid to liquid. So delta S fusion, that means that is basically again the delta, that is delta H of fusion divided by T. As in the earlier case, it was the vaporization, it is just the fusion. And delta V is basically the delta T of fusion is V of liquid minus V of solid. So what we do here is we rewrite this as delta H fusion divided by T times delta V or V of liquid minus V of solid. So now this condition, this is a condition that we cannot actually neglect as in the earlier case in this case. So we keep that intact, that is still, that is a change in fusion. So I write it Tp equal to delta H of fusion divided by T times delta V of fusion one by T dt. And if I integrate, so on integration I get the change in pressure delta P, that is equal to, that is a finite change from some pressure say P0 to P, that is delta P, and this is delta H of fusion divided by delta V of fusion times, if we integrate it, then we have log of ln some T by T0, some T0 to T, log of T by T0. Now, we can slightly change this quantity and approximate this quantity if we note that it is a constant, that is del H fusion divided by del V fusion times, there is a logarithmic quantity, and if I can approximate this in this way, say I write some T0 plus T minus some T0 in the numerator, and in the denominator write it T0. So this T0, T0 cancels out and I get back this T by T0. So if this is so, then delta P, change in pressure, is again delta H of fusion divided by delta V of fusion times log of, if I divide this is 1 by T0 minus T minus T0 by T0. So this is that I can write. Now I approximate these quantities as delta H by fusion divided by delta V of fusion times. Now if I expand log of 1 plus x, the first term is basically x. So this is basically the x. So this is T minus T0 by T0, and that is an approximation, of course, but it's a very good approximation because the change T machines T minus T0 equal to delta T much smaller than T0. So that this approximation can be done. So this is so this finally leads us to delta P, then delta T and that is equal to delta H of fusion divided by T0 times delta V of fusion. So if we know the change in molar volume as well as this delta H, I can find out the change in pressure versus temperature thing. So if I take T0 to be by normal boiling point, so normal melting point. So if that is the normal melting point, so this is a equation which is an analog for the case of solid liquid transition corresponding to this Clausius-Clapeyron equation which applies to liquid gas transition. So these are the typical ways we can use this Clausius-Clapeyron equation for our purpose and understanding the phase transition, that is one phase is goes over to other and they coexist, and during the coexistence if I change any of the parameters and how the other parameters has to be adjusted so that I can restore my new equilibrium. So that is the thing we can find out. So this is so with this we conclude here this point, and in my next lecture I will go over to the other aspects of phase equilibrium, that is how to draw phase diagrams, what are phase diagrams, and after that possibly the phase rule. So with this I thank you all for your attention.